So there are two main distance measures which are basically used in order to measure the distance between different data samples, and one of these distance measures is the Euclidean distance. So Euclidean distance between 2 points I and j is the length of the line segment connecting them. So we are basically measuring the length of the line which is basically connecting two data points. So if we talk about for the Cartesian coordinates, in Cartesian coordinates, if the one data point I is given as I1, I2 up to In, and the other data point which is Q, and it's given as Q1, Q2 up to Qn, then the distance d can be defined from point I to j, or from from j to I in through this expression. So in this expression, d is basically the Euclidean distance which we are trying to measure between these two data points, which is xi and xj. So as you know that the Euclidean distance is basically the subtraction of the data points and their summation under the root. So if I calculate this formula, the resultant will be the distance between the two data points, which is xi and xj. So this is simply the Euclidean distance calculation formula, which you have already studied so many times. Similar to Euclidean distance, another distance measure which we normally use to calculate the distance is the Manhattan distance, which is also known as the city block distance, right? And similar to Euclidean distance, we can use this formula in order to calculate the Manhattan distance between the 2 points, which is xi and xj here, right? So similarly, we will simply compute the summation, and this will give us the distance, the Manhattan distance. Similarly, we can compute the distances between different data points based on either Euclidean distance and the Manhattan distance, right? So depending upon the computation cost and the data samples and the problem which we are trying to solve, we can decide that which data point basically we want to use. So now let's look in which we will see that how can we evaluate the clusters, right? So clusters can be evaluated in two terms. One is the intra-cluster cohesion, and the other is the inter-cluster separation, right? And we can also write these as the compactness of the cluster, and the other as the isolation of the cluster. So in compactness, we are basically trying to measure the cohesive measure near the data points in a cluster or to the cluster centroids, and this can be computed or calculated as the squared error or the sum of the squared error, which is commonly used measure in order to find the compactness of the cluster. Similarly, if we want to evaluate the cluster on the basis of isolation, it means that the separation means that different cluster centroids should be far away from one another. And what is this cluster centroid is, we will look at it in detail when we will be looking into the k-means clustering algorithm. Then we will see that what does this cluster centroid means, and how we are trying to find a separation between these 2 points, and how we can see that the centroids of the two clusters are far away from one another. Now, one thing which we also discussed in previous slides, that how can we know that what is the optimal number of clusters for my problem. For example, we can have 3 clusters, or maybe we can have 2 clusters. So what is the possible approach through which we can find out the optimal number of clusters for a specific problem? So one thing which I also discussed previously, that we can also fix the number of clusters to k. For example, if I denote the number of clusters with k, then k becomes a hyperparameter of whose value can be selected based on some experimentations maybe, or through some prior knowledge, and the value of k will basically determine the number of clusters that the algorithm will be computing. Another approach is to find the best clustering according to a criterion function. So we can define a function in which the number of clusters may vary, and then that function will basically try to find the best number of clusters. And the three most commonly used approaches which most of the state of the art works uses in order to decide the number of clusters can be categorized in three categories. One is the visualization. So we can have visualization in order to decide the number of clusters, or we can also have some domain knowledge and maybe some data driven methods. So in visualization, sometimes you can determine the number of clusters by plotting the data. So what we do in visualization is we can draw a scatter plot of the data samples, and then by looking at the scatter plot, we can have an observation, a visual observation, which can tell us that okay, this much number of clusters will be a good approach for this problem. On the other hand, we can also use our previous domain knowledge for that problem. The knowledge about the application guides the choice of number of clusters, right? So if, for example, I am working on an application which is basically a spam detection application, then the problem domain basically is telling me that I want to have two clusters in which my emails will be classified as spam, and the other cluster can be in which my emails will not be classified as spam. So in this way, by having the domain knowledge of the problem, we can decide that how many clusters we want to have in our approach. Number third thing can be the data driven methods, and in data driven methods we can have some methods that calculate different matrices for the values of k in order to determine the best value for k. And the most common data driven method is an elbow method, right? So let's have a look at this elbow method. As you can see in this graph, that this graph is basically creating an elbow. That's why it is termed as the elbow method. And the elbow method helps us to determine the optimal number of clusters for a given data set, right? As the number suggests, and as shown in the figure, the elbow of the graph gives the best number of clusters for a given data set. So when we draw the number of clusters against an objective function, right, then we can see that which is the sweet point. So we are looking for a sweet point here after which my number of clusters are not changing drastically, right? So that's why this point can be treated as an elbow, on the basis of which we have named this algorithm as an elbow. So in elbow method, which is a method to determine the number of clusters, we are basically trying to figure out a sweet plot by plotting the number of clusters against an objective function, and we are basically looking at the point where the number of clusters are not changing drastically. So that point can be treated as the best number of clusters, right? So if we have 3 here, then we can conclude that for this problem we should have 3 number of clusters, and that will basically solve my problem in a better clustering way. So now the objective function is, which we are talking on this y-axis here, is that the marginal change in the objective function is very small as the number of clusters is increased beyond the elbow point. So we have seen that as we move away or forward from the elbow point, we see that the change in the number of clusters is not very much, right? It's a very slight change. thus making it the optimal operating point, or we can call it as a sweet point. Now the objective function is a function which helps us decide the most optimal point, right? So this objective function of course will vary from problem to problem and domain to domain, right? So depending upon the problem and domain, we can define our objective function, and we can plot a elbow based on that objective function.